Hello everyone and welcome to today's webinar. Before we begin, we want to cover a few housekeeping items. For any common technical issues, please refer to the Help widget located at the bottom of your screen. This webinar was pre-recorded and is being presented with a live Q&A. If you're tuning in for the initial webcast, you can submit questions via the Q&A widget on the left side of your screen. The researchers will be answering them via the widget in real time. Also, stick around after the webinar for the live Q&A, when the researchers will dive deeper on popular questions asked. Additional resources and links provided from today's presentation can be found in the resource list on the right side of your screen. An on-demand version of the webinar will be available approximately one day after the initial webcast and can be accessed using the same audience link that was sent to you earlier. On-demand viewers will get to hear the recorded version of the live Q&A. Enjoy the webinar.
Hello, everybody. My name is Josh Benaloh. I'm the Senior Principal Cryptographer here at Microsoft Research, and I'm going to be talking to people today about Microsoft's ElectionGuard technology, which allows people to verify that their votes have been correctly counted. So I'm going to start by talking about a report that was done a couple of years ago by the National Academies of Science, Engineering, and Medicine, looking at the state of elections in the U.S. We know that confidence in elections is at somewhat of a low these days, and we're looking at the situation and trying to understand what we can do to improve it. So the findings of the report included many elements, and I'll just touch on a few. First of all, there is abundant evidence, really no question about the fact that there was extensive Russian intrusion into the 2016 election, mostly in the form of disinformation, attacks on voter registration databases, and other forms of attack. However, it's important to note that there is no evidence that I've seen or the people I've spoken to have seen of tampering with the actual votes. Nevertheless, we know that our electoral system is extremely vulnerable. There are many ways in which tampering of votes could happen, and we want to talk about ways in which we can tell what's happening and deal with it. So we know that we must apply the best practices that we can in order to try to improve our voting systems, to try to bring things up to the best standards that we can. However, we know that this is not sufficient. And the reason is the challenge here is asymmetric. In the U.S., elections are run locally, mostly by counties, sometimes even by townships. There are only 2 states that run elections at a statewide level. Yet the attackers can be nation states. And it's simply not reasonable for us to expect that a small county government with likely a very small IT department can withstand an attack from the Russian FSB or APT-1 in Shanghai or North Korea or many other nation-state attackers. So we have to accept that, yes, we should do things to try to improve security, but that's just not going to be enough. We can't reasonably expect to make our election systems impervious to attack. However, even though we can't ensure that our election systems can't be attacked, we can detect it. And what it says is that auditing of elections is essential, and there are things that we can do to make sure that we know what's happened. So in this National Academies report, we recommended 2 particular kinds of auditing. One is a risk-limiting audit, sort of an administrative audit, and the other is a public form of auditing called end-to-end verifiability. I'll speak very briefly about risk-limiting audits. This is a fairly new technology to be more efficient about the kind of audits that you might think of traditionally. Traditionally in an audit, what happens is people will select ballots in some form at random and then see if these things confirm the tally, either by converging on the tally slowly or in better circumstances by matching them directly against electronic records. That can make it far more efficient. The risk-limiting approach uses more sophisticated statistics to make the audit process dynamic, rather than what we've traditionally seen where maybe there's a fixed percentage of ballots that are audited or a fixed percentage of precincts that are audited. A risk-limiting audit allows auditors to know how many ballots need to be checked in order to confirm the accuracy of the outcome of the election. The other kind of auditing that we talked about in the National Academy's report is a technique called end-to-end verifiability. And end-to-end verifiability uses cryptography to allow public auditing. Members of the public can check for themselves that the election outcome is correct, that their votes have been accurately recorded, and that all of the recorded votes have been accurately tallied. So to get into a little bit more detail about end-to-end verifiability, what end-to-end verifiability achieves is that any inaccuracies, any tampering in an election can be detected. And when I say can be detected, I'm not just speaking about detection by election officials. The detection can be done by candidates, by the media, by individual voters or other observers. It's a public verifiability. Anybody can check that the election has been properly conducted and is accurate. And this is not just limited to external tampering. This enables detection of corruption by election officials, by equipment vendors, by others, even kinds of tampering that have not yet been imagined. End-to-end verifiability enables us to see if the outcome of an election is correct. So at this point, I should give a slightly more formal definition. There are really two aspects to end-to-end verifiability. The first is that voters can verify their own selections have been accurately recorded. And then anyone can verify that the recorded votes have been accurately tallied. And this is more or less the most that you can reasonably expect can be done. You can't expect anyone to be able to verify that an individual vote matches the voter selections without knowing what that voter's selections were. And this would violate privacy of the ballot. So this is pretty much the most we can hope for. It seems very strong, but actually it's not that hard to achieve. So let me describe how we can achieve end-to-end verifiability very easily. Here is a public ledger of an election. All the names of the voters are listed. All their votes are listed. The totals are listed. And now anyone who voted can check to see that their vote has been accurately recorded. And anyone can look at this ledger and see that the recorded votes have been accurately tallied. It's actually a very easy thing to achieve. Of course, if you're thinking a little bit ahead, you may realize that I've kind of skipped something important and that there's no privacy in that public ledger. And privacy is critical to most elections, certainly public elections, secret ballot elections. It's a very strong requirement. It's not just that voters are able to cast votes in private. It's that voters must be unable to disclose their votes to others even if they want to. If voters are able to disclose their votes, then they can be coerced into voting in certain ways. They can sell their votes. They can do other things that we really don't want voters to be able to do. So to protect voters, voters should not be able to show anybody else how they voted. Of course, if we didn't have this requirement, the last slide that I showed would finish the talk. Things would be very easy. We can have a nice, secure bulletin board, a web page with everybody's vote, and we'd be done. Now, this is not something that is extraordinarily unusual. Most U.S. presidents were elected without the benefit of a secret ballot. Secret ballots are a relatively new technology, dating back to the 1850s, I believe, in Australia is where they were first used. And then in the 1880s in the U.S. Is where they first became prominent. It may not seem like a technological advance, but the idea of voters being able to vote within a public environment, but privately within that public environment, where their privacy is being publicly monitored and publicly enforced, was a new idea. Before that, we didn't really have good ways of having secret ballot elections, so we had what's shown in this famous portrait. People going to the public square and effectively announcing one at a time what their votes were. Of course, this creates a lot of problems, and this is something we want to avoid. So I'm going to go back to this public end-to-end verifiable election and show how we can take this and make just a small tweak to it and achieve a private, a secret end-to-end verifiable election. And the trick is basically to have the same public listing, but instead to encrypt all of the selections made by every voter, all of the actual ballots. So instead of seeing the actual selection made by a voter, you would see the encryption or an encryption of the selection made by a voter. Now, if we're showing only encrypted votes, we need a couple of things to achieve end-to-end verifiability. We need to provide a way for a voter, Carol in this case, to know that the encryption that corresponds to her vote actually matches her selection, Adams in this case. We also need to have a way of taking this list of encrypted votes and showing that these encrypted votes correspond to the announced tallies. Now, these are possible, and I'll show how to do them. But once we have that, we can achieve a secret ballot end-to-end verifiable election. So we have two questions that have to be answered. The first is, what do voters do to turn their preferences into encrypted votes? And the second is, how are voters convinced that the published set of encrypted votes corresponds to the announced tally? Okay? Those are the two issues we've had to deal with. And I'm going to deal with the second one first for a variety of reasons. It's sort of the more compact and mathematically rigorous. Also, the first historically in the history of end-to-end verifiability. So let's talk about encryption a little bit at this point. There are a lot of things that one can do with encryption, but typically encryption is a static thing. The only thing that's typically done with encrypted data is it is eventually decrypted. Now, it might be put into storage and then removed from storage and then decrypted. It may be transmitted from one person to another and decrypted by the recipient. It can move around a lot, but the encrypted data rarely changes as it's stored, as it's moved around. The only thing that is typically done with it is decryption. But that's not the only thing that can be done with it. It is actually possible to compute on encrypted data in encrypted form. Some encryption methods allow that computation to be done on two encrypted values. So you could take two encrypted values and combine them in some way to form a new encryption which represents some function of the two values. So this notion is typically called homomorphic encryption. And I'll give a couple of examples of how this can be done. First, it's possible for us to construct encryption functions such that if big A is an encryption of little a and big B is an encryption of little b, then if we multiply the two encryptions, we get something which is an encryption of the product of the plain text, the unencrypted values. Simple enough. And many modern encryption systems actually achieve this. If you know of RSA encryption, it has this property. We can also construct an encryption function that if you take an encryption of little a and an encryption of little b and multiply the encryptions together, you get an encryption of the sum. Now, you might think what you have to do is add the encryptions together, but for various technical reasons, it usually works much better to multiply the encryptions, but that will be an encryption of the sum of the initial values. Okay, so why is this interesting in particular when we're talking about elections? Well, in an election, if we take an encryption of the first vote, an encryption of the second vote, and go on through all the votes, all we really need to do is add up the votes. Tallying an election is nothing more than simple encryption, simple addition. So all we have to do is take the product of these encryptions, and we get an encryption of the sum. And the sum is our goal. The sum is the tally of the election. So let's take a look in a little bit more detail at what a ballot might look like. A ballot could be thought of as just a vector, an array of zeros and ones. Perhaps 1 means an option was selected, 0 means it's not selected. We might have multiple contests in an election and multiple options per contest. So in this ballot, we see in the first contest, the second option was selected. In the second contest, the first option was selected. And in the third contest, the voter chose not to select any options. Okay? So if we have a whole set of votes that are of this form, then all we're doing is adding up the columns and going down each column, getting the column sums. That's the tally of the election. Nothing more than simple addition of zeros and ones. So if we have an ability to do addition underneath encryption, where we've encrypted ballots, encrypted the votes, and then we can add them without decrypting, we can achieve something very valuable here. So imagine that these are now encrypted ballots. They're covered up. You can't really see what's under them unless you look very hard. Have special powers of some sort here. What we could do is multiply these encryptions together, again, by columns. So there's an encryption of every 0 and 1 here, and we're just multiplying down the columns and getting new encryptions down at the bottom. And then we decrypt just this amalgamated tally value at the bottom, and we're getting a tally, or actually a set of tallies in this election, without having to decrypt the original votes, the original ballots. Okay? So this gives a sense of what we might be able to do with this technique of homomorphic encryption in order to enable ballots to be kept private, kept secure, and still allow a publicly verifiable tally that looks the way it would have had all the ballots been opened in the first place. Okay, so there are a few things we need to mention about this encryption to get everything right. First of all, it's important to realize that this encryption is randomized. We never want it to be the case that two identical votes will encrypt exactly the same way, because then you could tell, oh, your vote is the same as mine because the encryptions are the same. So we need this randomization to prevent identical ballots from having identical encryptions. So the actual encryption method will take selections from a voter, will take some randomness, and put them together to form an encryption. And if you take a particular selection and particular randomness, you'll get a particular encryption. And if you change the randomness, you'll change the encryption, even without changing the selections made. So once we have that, we also have a way of creating a verifiable decryption of a ballot. As long as this encryption is done with some public method, public key encryption, then we can prove that a decryption is correct by just releasing the random information. In this case, if we say that Adams is the raw ballot and this random value is this long number that begins with 667, then somebody can put these things through the encryptor and see that they match the encrypted ballot that it's supposed to and say, oh, well, I guess that encrypted ballot really does decrypt to atoms. All we have to do is release this random value, and this random value serves as a key to the decryption. So who should be able to do this decryption? Compute these random values and figure things out. Well, we don't want there to be one single entity who can decrypt everything. That's much too powerful an entity. That entity could see how everybody voted, and we want to avoid that. So we want to split the decryption capabilities amongst some sort of a canvassing board. And that's the traditional group in elections in the US that makes decisions, looks at ambiguous ballots, and decides whether a particular vote counts or not. In most jurisdictions, there's some canvassing board or equivalent that maybe consists of 3 members or 5 members who make the decisions about the details of eligibility and other decisions in ballots. So this canvassing board is natural to be a group that is given this capability of decryption, and they have to work together to perform a decryption so that they could decrypt the tally of the election, say. So we want to split the decryption functionality amongst the members of this canvassing board, and it turns out it's not that hard to do it. But we're going to take this a step further. We don't want to require all the members of the canvassing board to cooperate in order to decrypt. There are things that can go wrong. It's just too many things that can go wrong. One of the members of the canvassing board could lose a key or hardware or a device of some sort that enables the decryption. Maybe one member of the canvassing board is unhappy for some reason, sees things are going in a particular way and doesn't like it, and refuses to cooperate to decrypt. So we want to build in a little bit of robustness. And what we'll do is use threshold encryption. In particular, since we're using homomorphic encryption, we have to use threshold homomorphic encryption, which allows us to set parameters and say there are 5 canvassing board members. We might want to say any 3 of them together can perform decryption. Or we could say 4 or 2. 2 is probably too small, but 3, a majority, is a reasonable number here. So we've talked a bit about how ballots are encrypted and the encryptions are tallied, but now we have to get back to question 1, what it is that voters do to turn their preferences into encrypted votes. And this is a little tricky, right? Because now you're asking humans to encrypt in some way. How can a human being turn preferences into an encrypted ballot? This seems like it's a hard task. But there are some tricks that make this possible. So I have a volunteer here who I'm going to work with to show how voters can be confident in the correct encryption of their votes. So what I have here is an ordinary deck of cards. I have no magical skills whatsoever, sorry to say. And there are really just 2 kinds of votes in this deck. There are red votes. There are black votes. This is a black vote. This is an encryption of a black vote. You can't see what this black vote is unless it's decrypted. So I'm going to ask you as a voter to select how you want to vote. So you have 2 choices, red or black. Would you like a red vote or a black vote?
Black.
Okay. So now what I'm going to do is put down several cards. And allow you to choose whichever card you want just by pointing to it. Don't touch it. Don't turn it over. Just
I'll take that.
Okay. So this is going to be your vote. So what I'm going to do is turn over this one, this one, this one, and this one. And now you can see that all the other cards that you didn't select were all black. Therefore, you have some reason to believe that this card is black as well. You don't have absolute certainty in it, but you have good confidence. The only way that I could have cheated you and had this be a red card is if somehow I had predicted in advance that you were going to choose this card, and my chance of doing that is probably not more than 20% in this case. So this gives you an idea of how I can convince you that your unseen vote, in this case, this card that you haven't seen, which you believe is black, but you don't know whether it's a club or a spade, you don't know its rank. I'll turn it over. It turns out to be the 6 of clubs. But at this point, you didn't know what it was, but you could follow this card through the system. You could virtually write your name on the back of it and follow it through the system and see that this is your vote and it's being counted. Now, of course, we're not really going to make multiple ballots for voters and ask them to choose which ballot to select. So what we really do with voters is something a little bit simpler, which I like to call the world's most boring card trick. So what I'm going to do is allow you to select a vote. I'll put down what I claim to be the correct vote and allow you to say whether or not you want to keep it. And we'll do that just for the sake of argument here. I'll encourage you to look at least a few cards, just to show things, although most voters will not look at any. So for your first vote, would you like red or black?
Go red.
Okay, red. Claim that's a red vote. Would you like to see it?
Yes.
Okay. Yes, it turns out it is a red vote. Okay, this time would you like a red vote or a black vote?
A black vote.
Okay. Would you like to see this one?
Yes.
It turns out to be black as well. Red or black? Black. Okay. Would you like to see this one? Okay. That one's black as well.
Okay.
Red or black?
Red.
Would you like to see this one?
Not this time.
See, I told you with the world's most boring card trick, you've gotten bored already. So this is going to be your vote. And because I didn't know where you were going to stop and where you were going to say, I want that vote and cast it, only if I had somehow guessed what card you were going to stop on could I have given you the wrong vote here. Could I have given you a black vote when you asked for a red vote without your noticing it? Now, this will be your vote. You could virtually write your name on the back of it and follow it through the system. You have confidence that it's a red vote, but you have no way of showing anybody else what it is. Again, you don't know whether it's a heart or a diamond. You don't know its rank until I reveal it, which I'm doing in this case just for show, to show that it really is what it was supposed to be. Thank you very much for your help.
Thank you.
The statistics are very much on our side here. The statistics say that it's okay if only a tiny, tiny fraction of voters actually take advantage of this option and spoil their ballots, even if very, very few voters do this in a sufficiently large election. So as an example, if 100 voters in a national election with maybe 100 million votes cast each spoil a ballot, and this is sort of randomly distributed throughout the electorate, then a malicious system trying to steal votes, trying to cheat in some way by flipping votes, will likely be caught if they try to flip more than 1% of the votes. And if I flip it around another way, if 1% of voters in an election check, then it's very difficult to imagine more than 100 votes being flipped without it being caught. So a very, very small percentage is enough to get very high confidence in the accuracy of an election. So what does an election record look like at this point? Well, we have various elements. We have all of the cast ballots and a mathematical proof that the cast ballots are correct, that they correspond to the tally that has been announced. We have all of the spoiled ballots and their decryptions. Voters don't need to individually check that the decryptions match their selections because, again, voters are not going to be able to do mathematics in a poll site. They're not going to want to. They're not going to want to check a decryption. But they actually don't have to. The decryption of their ballots is now public and part of a public record. So anybody checking the public record can check that the decryptions are correct. So even a diligent voter need only look and see, oh, I spoiled this ballot. And now I look at the public website and say, oh, that spoiled ballot is listed as corresponding to the selections that I made. And as long as that matches, that achieves a good challenge. And then the voter can leave it to others, or the voter can do by oneself the verification of all the artifacts produced in the election record. So the cast ballots, of course, we've seen this before. They correspond to zeros and ones in encrypted form. And if we open them, we can see that these cast ballots correspond to what we would get if we multiplied the encryptions, and that matches the summation of the original ballots. So the product of the encryptions of the cast ballots correspond to an encryption of the tally. And in practice, what we do is just multiply together the cast ballots and decrypt in a verifiable way that anybody can check that the decryption really does match the announced tallies. The spoiled ballots are also decrypted, and there are verification proofs included for all of the spoiled ballots and for the tally. So, what does this look like for a voter? Well, it can look pretty much like any traditional election system. It could look like walking up to a device that's got some nice accessibility features, maybe even an audio channel for voters with visual disabilities, and maybe brightness and other ways of changing contrast. And that device can be used to mark a ballot on a touch screen. Voter could also hand mark a ballot and put it into a scanner. Pretty much anything that you think of as a traditional in-person voting system can be used with an end-to-end verifiable system. But there's one addition in an end-to-end verifiable system, and that is the tracking code that the voter receives and gets to take home. So this tracking code might look like an encryption or something derived from the encryption of a ballot. It might say, here is where you voted and when, and here is your tracking code. Here is basically the encryption of your selections. Now, again, since it's an encryption, you can't use this to show anybody else how you voted, so it doesn't allow you to be coerced or to sell your vote. But it does allow you to track your vote through the system, make sure it hasn't been changed, and because you can spoil a ballot, you can get confidence that this encryption really does match your selections. So, from the voter's perspective, voters can use these tracking codes to check their results and make sure that their votes are properly recorded on a public website. And what we have found is that a reasonable percentage of voters seem to do that. If we make it easy, if the receipt says, here's this website that you can go to, a reasonable fraction of voters seem to go to this website and look up their tracking codes and make sure that they're there. Or do what probably most voters will do, is take these tracking codes, look at them maybe with a little question, crumble them up and throw them in the trash. That's okay. We don't need every voter to track votes. We just need a reasonable percentage of voters to engage in this step. Voters can also write their own election verifiers, where they will go through all of the artifacts produced by an election and make sure everything is correct, everything is consistent, and the tallies match up. They can do that I don't reasonably expect that most voters will, but some could. More likely, voters will just download verifiers from other sources and run them themselves and see, oh yeah, all the artifacts in this election check out. There are people who are writing verifiers right now for this kind of technology, and hopefully there will be many verifiers available so that you as a voter might not do this, but maybe your niece is taking a computer science class and wrote a verifier as a step in this class, and you get your niece's verifier and run it on your election, and it says good. Great, that's a good step. More likely, people will just believe verifications done by third parties, their candidates, their favorite political party, League of Women Voters, ACLU, other interest groups of various sorts, news media, and say, okay, you were able to verify this election, it's good. I'm happy. I didn't have to verify it myself. Or voters can do pretty much what they do today because they don't have any choice today, and that's accept the results with no question. They can just say, okay, here it is. I don't care. I don't have to do anything. It's critically important that we not force voters to do anything that they're not doing today. We're just giving them new capabilities. So, what's in one of these verifiers? Well, there are a few things that have to be included. Verifier, first of all, has to check that the cast ballots are correctly combined to form an encrypted tally. It's just checking the multiplications. So if we look here, it's basically saying, okay, all these columns multiply out to the bottom. And it's just a simple check, but anybody should be able to check that. A verifier also should check the decryption of the tally, make sure that's correct. So that's just opening that, making sure that that does match with the artifacts that have been provided. A verifier should verify that all of the spoiled ballots were correctly decrypted as well. So that's this step over here, where you take all the spoiled ballots and you open those, and the verifier should go through and make sure all of those spoiled ballots were correctly opened. But there's one more step that I'm leaving out, and this is perhaps the most subtle. I often can go through and talk about this without anybody thinking of this and realizing it, but some of you may be thinking this is important right now. And that is, verifiers must check that every encrypted ballot is well formed. What do I mean by that? Well, we showed earlier what a ballot might look like. It may look like a vector of zeros and ones. So this is what a valid ballot could look like. Here's a ballot that might not be valid. Maybe this ballot has 2 votes in the first contest, and in this election you're only allowed to vote once in the first contest. There are some elections where it's okay. You can vote for up to 2 or up to 3 or something like that. But if this is an election where you're only allowed to vote for 1 selection in the first contest, and this ballot has 2 selections made in the first contest, it's not valid. Let me show you another invalid ballot. This one is definitely invalid. One where there are 101 votes in this one ballot cast for the second option, and negative 100 votes cast for the fourth option. So the totals will match up, and the total number of ballots, the total number of votes will match up if you have even one single ballot in an election that looks like this. But of course, the tallies will not be correct. So one critical thing, and this is where most of the work in a verifier is to go through a ballot, every ballot in fact, and make sure that every encryption on that ballot is either an encryption of 0 or an encryption of 1 without knowing which, and there are ways of doing this. There are non-interactive zero-knowledge proofs is the technique that's used here. And these proofs are provided to show that each selection is either an encryption of 0 or an encryption of 1 without showing which, and the verifier will go and check that this proof is correct so that every entry in the ballot is well formed, that the number of selections made in any contest doesn't exceed the limit of the number of selections made. And once you have that, you really do have full verification. So there are really just 4 operations that need to be done in a verifier. The first is modular addition, adding things mod a prime in this case. Modular multiplication, just doing a multiplication and taking that value, modulo, again, another prime. Modular exponentiation, raising a base to a power mod, again, a prime here. Of course, this, with the large numbers that we're using, can't be done by just exponentiating and then reducing. You have to have some sort of a tool that will go through and do this modular exponentiation with reductions as you go. And the final tool that needs to be included in a verifier is a Sha-256 hash. This is a standard hash function. These are all readily available. There are packages in many languages that'll do this. Python has modular addition, multiplication, and exponentiation of large integers built in, but many other languages have this. So it is a reasonable task for you as an individual, or maybe you as a professor, to assign to a student, either as a class project or an independent study project, to write an election verifier that uses these technologies and can be used by the author and by others to verify elections. So, more information is available. ElectionGuard has been deployed as an open source, free toolkit. Microsoft is working with election vendors to build ElectionGuard into new and existing systems. We're not trying to make money out of this. This is not something that we're selling. This is something that we're doing for public good. And we are encouraging vendors to use this and working with vendors to try to get the details right. And the toolkit is available at github.com/Microsoft/ElectionGuard. There's a detailed specification that goes through all the mathematics and all the organization and the structure. That's also available on that website. And there is a verifier that has been written in Rust as a reference that is also available. We have run our first public election with ElectionGuard. It was done in Fulton, Wisconsin, and seemed very successful. And that was our first pilot. We are looking to have many more pilots and try to get this technology as widely deployed as possible. End-to-end verifiability is a great tool for enabling members of the public to check that their votes have been properly counted. So thank you, everyone. If you'd like to stay around, I will be answering some of the best questions that have been submitted, and hope to explain more about this technology and give you a chance to understand it and use it for yourselves. Thank you.
All right. Thank you, everyone. Thank you for listening. This is Josh Benaloh, now with you live. I hope you enjoyed the webcast, and I'm going to try now to answer some of the questions that came up. A whole bunch of questions came up at the last moment, so I've tried to look over them. But if I don't get to your question, my apologies. You can try to talk to me offline if anything is not fully addressed here. The first thing I would like to try to address is that there were many questions having to do with the process of spoiling ballots. So I want to try to clarify that a little bit. That was described a little bit in the card trick that was done, but I'd like to give a better sense of how that fits into the actual process of voting. So this is intended, by the way, principally for in-person voting, although I can talk a little bit more about some alternatives. But imagine that somebody is voting in person and they go through a process. Maybe they're working with a device, an electronic device, and they're making their preferences known. Maybe they're hand marking a paper ballot. There are a variety of mechanisms. They complete the process. They then go to the next step of partially submitting this vote. It would perhaps be the last step on a screen, or might be putting a hand-marked ballot into a scanner, and they would at that point receive a tracking code. Now, that tracking code is a commitment to the ballot that they have created, but it is not yet representing a cast ballot. Voters still have an opportunity at that time to cancel their ballot and restart and retain the tracking codes that they have received. So a voter could at that time spoil or cancel a ballot. Spoil is kind of a term of art in the election industry that just says, I want to cancel a ballot and restart it. So they would have an opportunity to cancel their ballot and then restart and submit a new ballot. And they could even cancel the second ballot. Now, we do not by any means require every voter to do this. A very small fraction of voters, probably fewer than 1%, will actually spoil ballots. And ballots might be spoiled for a variety of reasons. It might be that a voter spoils a ballot as part of the process because they look at the end at a paper ballot and they say, well, I made a mistake. I want to spoil my ballot and restart to correct it. Or they might spoil a ballot to actually create an explicit challenge. And either way, it works with the system by saying spoiled ballots will be opened. There will be no names associated with them. There are no names associated with any ballots in general. But the spoiled ballots will be publicly open, decrypted, and they serve as a check in the same way that the card trick described. Anybody who spoils a ballot might be doing so to just test to make sure that it opens, it decrypts in the way that they expect and hope. So that's the principal reason that we have for spoiling, and the principal mechanism that is available for spoiling is just that in person you decide, I think I want to challenge one ballot, or maybe even a super diligent voter might challenge a second ballot, and make sure that those were encrypted correctly, and that gives confidence in the system that it's encrypting the cast ballots correctly as well. Okay. While I'm mentioning that, I will say a few things about the mode of voting. It's easiest to think of this for in-person voting. The technology can be used for internet voting, although we are not recommending it because there are other challenges with internet voting. As I think I said, internet voting, if you're going to do it, you really should use this technology. The U.S. Vote Foundation had its report saying that you must use this technology if you're going to do responsible internet voting, but that it's not sufficient. There are still other challenges, other problems that need to be solved, voting over the internet or via smartphones or any other remote voting scenario of that sort. Vote by mail actually can also be done with this technology, but the challenge is how would you do this cancellation spoiling process. There are a few tricks, there are a few possibilities. I'm not going to go into it now, but I'd be happy to speak with people offline if there are thoughts and ideas about what you might want to do in your local jurisdiction. We are trying to work with many jurisdictions right now and many vendors right now to encourage interest. It's, of course, a very challenging time. 3-4 months ago, people were a lot more interested in innovation in elections. Right now, the interest is a little bit more towards surviving elections. So the things have been slowed down a little bit, but this is a long-term goal. We are probably not going to have tremendous change, tremendous use of this technology for 2020, but we'd like to see it deployed as widely as possible for 2022, 2024. Another question that came up a couple times was homomorphic encryption and the use of it here. I should explain it a little further because homomorphic encryption can mean a couple of different things. It's actually a very old technology, dates back more than 30 years. I believe I was actually the first to use the term homomorphic encryption, although I'm not 100% sure of it. And I don't want to take too much credit for it because there was actually a paper written by Revest, Edelman, and Dutuzos on privacy homomorphisms. And when I needed to use the technology in encryption and decryption rather than just for privacy functions, it was a natural term to apply because it had been there. But anyway, it's existed for more than 30 years, but it was always kind of a niche thing because you could do it with one operation, you could do it with addition or multiplication, but not for general computation. Just over 10 years ago, Craig Gentry discovered a way of doing fully homomorphic encryption, which is homomorphic encryption that can do both addition and multiplication on the same encrypted values. And once you have that, that's what's called expressively complete. You can actually do any computation. It's a very powerful technology. The problem is that fully homomorphic encryption is much, much slower. Originally, it was absurdly slow and you couldn't do any computations at all. It's been improved a great deal over the last 10 years, but still, except for fairly simple computations, it is very slow, very cumbersome, adds a great deal of overhead, and is just not practical except for fairly simple computations. But that's not what we're doing here. We're using simple homomorphic encryption that predated fully homomorphic encryption. It's very, very efficient. It's just doing additions and nothing more. So that makes this much, much easier to do. Let's see. Another question that came up a couple of times was on verifiability in VVPATs. Some people call it voter verified paper trails or paper audit trails. This exists in some places, but it's certainly not enough to do end-to-end verifiability. End-to-end verifiability goes to the heart of the system and allows you to check not just that your vote is on paper somewhere and was supposedly counted correctly. It allows you to actually check the counting and make sure that your vote is amongst all of the votes that were counted, that your vote was correctly encrypted and matches your selections, and that the encrypted votes were accurately tallied. And all of this, of course, with the critical factor of your not being able to show anybody else how you voted, so that you can't be coerced, you can't sell your vote. These are critical to any election, and we need to make sure that we've covered these very, very carefully. Let's see. Another question that came up a little bit is on the zero knowledge proofs. I mentioned briefly the challenges of how to actually prove that ballots are well formed. I didn't go into that at all. There's existing technology in the field of cryptography for proving information about encrypted values without revealing undue information. So there are techniques due to Schaum-Pedersen, Kramer, Damgaard, Schumacher's, others that allow you to do things like prove that an encrypted value is an encryption of a 0 or a 1 without revealing which. And that's what's done here, and that is what can be checked by a verifier. There were also a couple of questions about verifiers themselves and how hard they are to write and who can write them. I'm currently working with students at a few universities to write verifiers. The first few will probably be a little bit more challenging as we get some of the bugs out and address some of the more difficult things. But this should not be too hard a thing to do. This is the sort of thing that a student can do as a small student project. And the expectation is that there will be many verifiers out there. So if you'd like to learn about this more, look at the spec, look at what's in GitHub. We have a sample verifier there, and you can use that. But I encourage anybody who's interested to go through and see exactly what needs to be written and write their own election verifiers in order to check elections. And once you write a verifier, it's not just for a single election, it's for all elections using this particular design. Of course, end-to-end verifiability can be done in many different ways, and there might be different parameters and different uses. But if we take ElectionGuard as it currently stands, that is one system, and one verifier for ElectionGuard can be used to verify many, many different elections using this particular technology. So the hope is that we will have many verifiers out there, and that people who are interested in doing so could download verifiers either from random sites or from sites that they trust. That I certainly wouldn't encourage running something off of a random site that they don't trust. But you can download these things as apps, and they can be contained and firewalled if you're concerned about them, and run them against any elections that you are interested in to verify that the election was indeed conducted properly. A question that came up is, what if one verifier says everything is good and another verifier says it's not? And the answer to that is that verifiers should not just say yes or no. Yes is a perfectly good answer. I've checked everything. This election is good, has no problems. All the artifacts check out. But just no is not an adequate answer. A verifier that just says, no, there's a problem without specifying what the problem is should be ignored. A verifier should instead, if it finds a problem, be very, very specific about what the problem is and say that this particular artifact is supposed to do this according to the spec, and it doesn't, and it could actually go right down to a single operation and say the specification says that these two values should add together to form this third value, and they don't. You can think of an election record as a spreadsheet. An election verifier is just going through all the cells of the spreadsheet and make sure that all the equations that calculate all the cells are indeed correct. So these are the main things that need to be done. And we hope that in coming years we'll see many instances of verifiers used for verifying many elections using this technology, so that voters can have better control, better confidence in the elections, and can check. They don't have to depend on others. They don't have to depend on equipment or hardware or software or even people out of their control to check the integrity of an election. they can check it themselves, or they can choose who they want to trust and proxy their trust in that way. So again, thank you everyone for your time, and we have some additional resources that are in the bottom right of your window that you can look at, or you can look me up and get in touch with me if you have some further questions that you'd like answered. I may try to reach out to individuals if there are questions that I wasn't able to answer. But I hope that you found this of interest, and I hope that you will vote in your next election, and that you'll vote in November if you're in the U.S. or wherever else you are at every opportunity, and that you'll be able to vote with confidence. Thank you very much. Have a good day.